Hello, can you hear me? Hello.
Yes, sir.
Okay. Good morning.
Good
Good
morning,
morning
sir.
to all. Okay, okay, thanks. Um, I'll just share my screen. Okay, so today we'll start our next unit, torsion of circular shaft. So, as the term indicates, that torsion is something related to twist. So, to twist, will transmit torque through using some circular shaft. So this is commonly used in our Excel of our these vehicles, and so we are interested in calculating the torque of torque transmitted because of torsion effect. So let us start our this lecture. So torsion of circular shaft. So a shaft is said to be in torsion when equal and opposite torque are applied at two ends of the shaft. So when we apply two equal and opposite torque, so it is said to be in torsion. Torque is equal to product of force applied and the radius of the shaft. Due to application of torque at two ends, the shaft is subjected to twisting moment. This causes the shear stress and shear strain in the material. So what is all written is that a twist is generated, and because of this twist, we have shear stresses, and because of this shear stress, our axle, you can see axle in truck. So because of this shear stress, this axle may fail, and so we are interested in calculating this shear stress as well as the torque transmitted. So first we will derive the this expression for shear stress because of effect of torsion. So let us proceed towards this derivation. So when a circular shaft is subjected to torsion, shear stress are set up in material of a shaft. To determine the magnitude of shear stress at any point, consider a shaft. So we have considered a shaft. If we look from the side view of the shaft, it will look like something B, and you can see here that AB. And if you look in from the front view, it will be a circular this geometry. So we have considered that one end, that is A and A, you can see one line over there, A and A, that is fixed, and we will provide a twisting effect at point B and B, which is at length from A and A. So I'll just read out what I have said. Fixed at one end AA and free at end BB as shown in figure. Let CD is any line on outer surface of the shaft. Now let the shaft is subjected to torque T at end BB as shown in figure. As a result of this torque T, shaft at end BB will rotate clockwise, and every cross section of the shaft will be subjected to shear stress. So because of a torque which we apply at at BB point, so every circular cross section will be subjected to some twist and resulting shear stress. The point D will shift to some other point, that is, let us assume that D dash, and hence line CD will be deflected to CD dash. In next figure, we will see that this D point has been shifted to D dash. You can see here from that. So as shown in figure, line OD will be shifted to OD dash. So line OD will be shifted to OD dash. So these are some of the parameters which we are considering for derivation of shear stress in a circular solid shaft. So if we assume R is the radius of the shaft and L is the length of the shaft, T is the torque applied at end BB, tau is the shear stress induced at surface of shaft due to torque T, C is the modulus of rigidity of material, phi is the angle, D C D dash also equal to shear strain, and this is also equal to shear strain D C and D dash, and phi is the angle of the twist. So phi is the angle of the twist, sorry, theta and phi. There's are two different uh, uh, terms. So from here we will proceed toward derivation. Shaft is fixed at A and subjected to torque at B and B. Now distortion at outer surface due to torque is equal to D and D dash. So if you look from the top view, and you will find one point that is we have assumed that D point, it will shift to some point D dash because of application of this torque or twist. So shear strain at the outer surface is equal to distortion per unit length. So if you look from the top view, this point D will shift to D dash, and because of which we can easily calculate the strain. So change is D and D dash, which we have written here, and divided by corresponding length L. So which is nothing equal to 10 pi. And for the small values of 10 theta, we assume it to be phi. Shear strain at outer surface is equal to phi D dash upon L, which is equal to 10 phi if angle is of considerable this magnitude. Shear strain at outer surface is equal to phi equal to D dash upon L. So phi is equal to R upon this L. If you look into the corresponding values, this will be equal to R into theta upon L, because R, you know that it is R is equal to angle is equal to arc upon radius, and correspondingly we have written this term. And once you substitute the value of phi, you will get R theta upon L. So coming on to the this definition of modulus of rigidity. If you look what is shear modulus or modulus of rigidity, this is shear stress induced upon shear strain produced. So shear stress, if we take value as to be tau and strain as r theta upon L, so this will turn out to be something given in equation number 8. That is, we have expressed shear stress in terms of our known values. That is, shear modulus is theta, r, and L. So we can see here this other terms C, theta, and L. If they are constant, then torque is directly proportional to this capital R, or alternatively we can write as E upon R is equal to constant. And if we are not assuming if we assume some inner point, uh, R is the extreme radius, but if we assume some inner point, small r, that is distance from center, then this will turn out to be tau upon r is equal to q upon r. This is tau upon r is equal to c theta by L. So this is our well-known this equation. We have also done it in while performing the experiment on the torsion. This is tau upon r, and this is theta upon L upon q upon r. So from above equation, it is clear that shear stress at any point in shaft is proportional to distance of point from axis of shaft. Hence, shear stress is maximum at outer surface and same is zero at the axis of the shaft. So shear stress will be 0 at the axis of the shaft, that is at the center point, and this will be maximum at outer surface. So assumptions made in the derivation of shear stress produced in circular shaft subjected to torsion. Now we are specifically talking about this circular shaft, because this circular shaft is okay. This circular shaft is commonly used in our this most of the material this machines, and therefore we need to have a this idea of what is the magnitude of shear stress and how we can design this shaft so that we can minimize this shear stress with the use of minimum material. So these are some of the assumptions. Material of the shaft is uniform throughout. Twist along the shaft is uniform. Shaft is of uniform circular section throughout. Cross section of the shaft, which is plane before twist, remain plane after twist. So it will not come out of the plane. All the radii which are straight before twist remain straight after twist. So radius will even not be distorted. So these are some of the assumptions. Based on this, if we assume maximum torque transmitted by the circular shaft is obtained from maximum shear stress induced at outer surface of the solid circular shaft, consider a shaft subjected to torque T. So we are always interested in determining the maximum value, and if we assume that tau to be maximum shear stress, which occurs at extreme that is outer surface, where the radius of is shaft is capital R, and let Q be the shear stress at distance R from the center. We have assumed any distance R from the center of the circular shaft, and the shear stress is small q. So let us consider an elementary ring, which is having this uh, area as 2 pi r into dr. So from our basic principle, we know that tau upon r is equal to q upon r. So in numerator, we have this maximum shear stress at distance capital R. There's in right hand side in the numerator we have a shear stress at some orbit distance, let us say at distance r. So we can rearrange this. We can write q is equal to this tau upon r into r. So this is the shear stress. In order to convert a stress into a force, we need to multiply with some area. Since we have assumed an elementary ring which is having area 2 pi r into dr, so we will corresponding multiply this shear stress with the corresponding area, and this is a turning moment which is of a small magnitude, that is dt, and the value of which is dt is equal to tau upon r into 2 pi r into dr into r. So first we have calculated shear stress, then we converted this shear stress into corresponding force. The next thing we did is we converted this force into corresponding torque by multiplying one radius, that is small r. Since this is a small value of magnitude dt, but we are interested in calculating the torque induced in whole of the this shaft. So we will integrate this value from 0 to r, and which in turn will come out to be by integrating, it is tau is equal to tau into pi d cube upon 16. So on in the left hand side we have the torque generated, and on right hand side these are the it is expressed in terms of the corresponding shear stress and capital D, which is the diameter of the shaft. So one thing we will are interested to note here that this is a case of solid circular shaft. That is, it is having material throughout its this length dimensions. So, can any one of you suggest me if I want to do same derivation for a hollow circular shaft? If I need to determine the value of torque for a hollow circular shaft, what changes I need to do in this derivation? Some one
I
of you
want
can
to add to
suggest me if
integration.
Sir, limit inner radius to outer radius in case of
yes,
0 to
yes,
r.
yes, yes. Yes, so if I change this limit, that is, if limit, if r I, if I assume some inner radius as r I and outer radius as r o, then limit will be from r I to r o. So, if you have said this correctly, can you please give me the expression for the torque in terms of inner diameter di and outer diameter do for this hollow circular shaft? Some one of you can derive it for me and quickly give me the expression. Acha, before the proceeding towards this, can anybody answer this question? Why we are doing it for hollow circular shaft? Any one of you?
Because hollow circular shaft is more stronger than a solid circular shaft.
Okay. And more advantage, what could be another advantage of using hollow circular shaft in comparison to solid circular shaft?
Lightweight.
Lightweight, correct. But what in terms of economic point of view, economy point of view?
Cheaper.
Less material, so
Cheaper,
less
Less
cost.
material use.
less material. Okay, it will be cost saving for an industry. Okay, so why don't you give one this expression for the T for the hollow circular shaft? If you have said this correctly, that limits are going to be changed. So let us
सर
see who is going to
इनिशियल
be.
एक्सप्रेशन में डी क्यूब के जगह डी
हाँ हाँ,
4 - स्मॉल d4
हाँ
बाई डी हो जाएगा.
करेक्ट करेक्ट, बिल्कुल ठीक है, करेक्ट. तो इनिशियल एक्सप्रेशन में हो जाएगा पाई बाई 16 टाउ d4 माइनस स्मॉल d4 अपॉन d4. ओके, तो अच्छा, कैन यू क्विकली गिव द आंसर फॉर दिस क्वेश्चन? You can write in the chat box. So you can solve it easily. I will show the solution. This will come out to be 29820. This is a straight away if formula. You have to simply substitute the values. This will come out 29820.586 Newton meter. So let us proceed towards this next question. Can you solve this problem? This is a solid shaft or diameter d diameter used to transmit torque. Find the maximum torque that can be transmitted if maximum shear stress induced in shaft is 50 Newton uh, uh, per mm square. So this is again a straightforward problem. So take 2 minutes time and please give the answer for this. If you will work on this problem, then okay, I do not have the answer. You can easily work out for this problem. All the values are given. So, as you have already told that this derivation, which we were supposed to do, transmitted by hollow circular shaft. So, I am not going into the details. You correctly said that we will be changing these limits of integration, and on solving, we will get this d naught raised to power 4 minus di upon d0 d naught. So next, when this small expression about the power transmitted by the shaft. So once we know the torque, we are very much interested in determining the power, which is 2 pi nt number of rpm upon 60 watts. So we can express it also in terms of angular velocity, that is tau into omega. So this is our last problem for today's class. Can you give the answer for this question? Okay, if you will work out for this magnitude of the torque, you will get this value 136.2 Newton per mm. Okay, so with this, we have almost covered this unit of torsion. One a small derivation is left, which we'll take in our next class. So I'll stop here.